The graph we closed with on Friday, we found out which vertices in that graph were eccentric to something else. So I'd like the same question to be answered here. To do that, I need two things. I need the eccentricity of every vertex here, and then I need to know which things are eccentric to what. Now, by symmetry here, you can really get away with only checking the eccentricity of three vertices. Because if you know what's happening on S, you know what's happening on T. You know what's happening on U, you know what's happening on W, and X and Z. And if you know what's happening on V, you know what's happening on Y. So what's the eccentricity of S, U, and V? S is 4. V is 2. Okay. So now the question is S eccentric to something? Is there something whose path to S is the same as the eccentricity of that item? The eccentricity of T is 4, takes me 4 steps to get to S, and vice versa, right? So S and T are both eccentric to each other. In vertex that U is eccentric to. Say again? Z. 1, 2, 3. Z to Y to V to U. Distance of 3. Therefore, similarly, U to Z. Z is an eccentric vertex. X to V to W and W to X. So all 4 of those are eccentric in diagonal pairs. Is there any vertex whose distance to V is the same as the eccentricity of that vertex? V is only 2 units away from everything except Y. And the eccentricity of none of the other vertices is 2 except Y, and the distance from Y to V is 1. So there's no other vertex away from V whose distance to V matches its eccentricity. V is not an eccentric vertex. Same thing with Y. In our previous graph from Friday, every vertex was an eccentric vertex. Here, 2 of them aren't. If every vertex is an eccentric vertex, I have an eccentric graph. Otherwise, I can induce a subgraph. made up of the eccentric vertices. The eccentric subgraph, ECC, eccentric of G. So if that's my graph up there, G, that just went off the top of the screen, the eccentric subgraph looks like that. So the one we ended with last time was an eccentric graph because every vertex was eccentric to something. This one is not. Okay. I asked the same question I asked about center and periphery. When can I know that a given graph is the eccentric subgraph of something? Like, how do I know if a graph is the center of something? How do I know if the graph is the periphery of something? Well, it turns out that the same exact result for periphery holds true for the eccentric subgraph. What was the condition on the periphery? That was the definition. But I said we could know that some subgraph was the periphery of something else if there was a condition. Exactly. Either every eccentricity of the vertex had to be 1, or none of them was 1. Well, it turns out that it's the exact same thing for the eccentric subgraph. And lo and behold, none of those eccentricities are 1. Or they all are. Now, our definition of eccentric was that we had an eccentric vertex if we could find something that was furthest from it, right? There was a vertex that it was furthest from. Match the eccentricity. V is the furthest away you can get from you. So if you took any neighbor of V, what do I know about the distance from W to U. It's got to be closer, right? I took one step away from V. I can't go further away. No vertex of G is further from U than V. Now, that sounds like a good criteria in and of itself to have. Hey, these are the vertices that are further away. If I take a step in any direction, I've got to have gone closer in. Closer in. If I'm as far out on an object as I can be, I'm on the edge, right? If I take a step in any direction and stay on the object, I have to be moving in. That makes that spot I was at part of the boundary. I'm going to call this a boundary vertex. V is a boundary vertex of U. If I go to any neighbor of V, I'm closer to U. Therefore, a boundary vertex on a graph is any graph where I can find such a U and V. Sorry, any vertex. So a vertex is a boundary vertex of a graph if it's boundary for some specific vertex. Okay, wait a minute. So now I've created three definitions between Friday and today. I have peripheral, eccentric, boundary. What was the relationship between peripheral and eccentric? Say again? That's how we defined the periphery. But if a vertex is a peripheral vertex, then it must be an eccentric vertex. But not the other way around. We could have eccentric vertices that weren't peripheral. We just did that right here. The periphery of that graph is only S and T. But the eccentric vertices include U and X and V and Z. Sorry, W and Z. So there are more eccentric than there are peripheral. But every peripheral is in the eccentrics. What about boundaries? eccentric vertices are automatically boundary vertices. However, the reverse is not true. Gesundheit. Once again, I ask you to write down eccentricities of all of these vertices. I need some eccentricities. So the periphery is U and Y. Let's take a look at W. Z is eccentric to W. Y is eccentric to W. U is eccentric to W. So all three of those are eccentric vertices. Only two of them were peripheral, right? So there are more eccentrics than there are peripheral. Peripheral, eccentric. W is a boundary vertex for S. I beg your pardon? W is on the boundary of S. Consider all the neighbor vertices of W. What are the neighbor vertices of W? Okay. The distance from S to W is 1. Go to any neighbor of W. If you go to S, the distance to S is 0. I got closer. If you go to V, the distance to S is still 1. It isn't further away. The distance to X is still 1. Moving to a neighbor didn't take you any further away. You're on the boundary. W is not a peripheral vertex. It's not an eccentric vertex, but it is a boundary vertex. There are even more vertices in the set of boundary vertices. Periphery, eccentric, boundary. The distance to the periphery is the biggest eccentricity. The distance from a vertex to an eccentric vertex of that U is the farthest we can get. The maximum possible distance you get away from U. That's the absolute maximum. But a boundary is a local maximum. The distance from S to W doesn't get any bigger if you move to a neighbor in the local neighborhood. There's between a local extreme and a global extreme. That's a calculus idea. Who the hell stuck calculus in this class, damn it? Intuitively, if I start at some vertex U, when I reach a boundary of U, no matter what neighbor of U I get to, I'm not any further away from that point. Being a cut vertex means you can't be a boundary. Wait a minute. If I can't be a boundary vertex, I can't be eccentric. And if I can't be eccentric, then I can't be peripheral. All cut vertices are excluded from the periphery. Because every peripheral vertex is eccentric, and every eccentric vertex is a boundary. So if it's not a boundary, then negation goes all the way back. So when I look at these subgraphs, the induced subgraph, the eccentric subgraph, the peripheral subgraph, I haven't really looked at a boundary subgraph because that's a little harder to create. But what I can look at are these extreme ideas. And really, a boundary is an extreme. So let's look at another definition. A vertex is a complete vertex, also called an extreme vertex, also called a simplicial vertex. Now that comes from the word simplex, which is a geometry term, which you may or may not hear next semester. But a simplex is like a building block in however many dimensions. A complete vertex is one whose neighbors form a complete subgraph. Help me understand why that's true. And the complete graph of the neighbors is just an isolated vertex, isn't it? Here's my leaf. This is the only vertex adjacent to it. That's a neighborhood all on its own. That's a complete graph on one vertex. Kind of boring because it has no edges. Because it's the end of the P2. Perfect. So let's suppose we have a complete vertex, V, and we pick an element of its neighborhood. By the fact that that neighborhood is a complete graph, the distance from W to U equals the distance from W to V equals 1 for every W in the neighborhood. That's what it means to be a complete graph, right? You move to any neighbor, you're still one step away from all the other neighbors. The neighborhood is complete. If I move to any neighbor, my distance didn't go up. What does that make my complete vertex? It makes it boundary. A complete vertex is not only a boundary vertex for every one of its neighbors, it's a boundary vertex of every other vertex. Complete vertices are always part of the boundary. Centric and peripheral vertices either came about from all having eccentricity 1 or none having eccentricity 1, right? Boundaries require a little bit different. A graph is non-trivial if it has edges. Let's take a vertex U. If that eccentricity is 1, then every other vertex is a boundary vertex. Well, wait a minute. Why is that true? Not necessarily all the other ones, but this one has eccentricity 1. U itself has eccentricity 1. I claim every other vertex is a boundary of that one. Definition of a boundary is that if I go a step away, I haven't made my distance go up, right, Reese? Again, I don't know that everything is eccentricity 1, but I know that all of the other vertices, this one is eccentricity 1. It means the furthest distance you can get from this vertex is 1 step away, right? So if you step to something else, if there was not a direct path, then there would be a path of length 2, wouldn't there? That would mean there'd be something that was further away, and I can't get any further away. That means that every other vertex that I step to has to be 1 unit away from you. It means the neighborhood has to be complete. If it's a complete vertex, then it's a boundary vertex. This statement right here is a consequence of this one. This doesn't seem to be making the idea of a boundary any clearer, right? The boundary still seems kind of weird to me. Peripheries are the ones with the biggest eccentricity. Eccentrics are the ones where I can find something that's exactly that far away. Boundary is still kind of squishy. I don't like it as much. We'll define not boundary. I feel like I'm the cat in the hat. The best way to find out what something is to find out what it's not. Okay. So let's take 2 distinct vertices, 2 different vertices in a graph. A third vertex, different from both of those, lies between x and z. If the distance from x to z is exactly equal to the distance from x to y plus the distance from y to z. Okay, wait a minute. I've seen that with less than or equal to before. What was the less than or equal to version called? Triangle inequality. When is your triangle not a triangle? when all three of your vertices are on the same straight line. Instead of having dot, dot, and then another one way off to the side, they're all lined up, and the distance from x to z has to go through y. The geodesic from x to z is the sum of the geodesic from x to y and y to z. It's in line with, it's in between. Okay, I get the intuitive idea here. I like this. I'm going to define the interior vertices of a graph. V is an interior vertex if there exists distinct vertices U and W so that V lies between U and W. So the interior vertices are the vertices that are between things. I'll take the collection of interior vertices and call that a subgraph. And that'll be the interior of my graph. Okay, wait a second. Which vertices of this graph that we've seen before are interior? There's my definition of being between. The interior vertices are the vertices that are between things. That are not. I agree with you that the end vertices cannot be interior vertices. Z, U, and Y are definitely not interior. But there's more. Because I've got 4 vertices left. Are all of them between? Why not, Ben? Agreed, S is definitely not between U and Y. But S is between Z and W. The distance from Z to W is 2. The distance from Z to S is 1. The distance from S to W is 1. In the same vein, X is between W and Y. V is between W and U. The only vertex I've left out that isn't an end vertex in one of those 3 is the vertex W. I claim W is not between. Because the distance from U to Y is 4, right? But I can avoid W altogether and still have a path of length 4. Not required to be between. U. Whoa. So it turns out that those 3 vertices are interior as opposed to all 4. Guess what? The boundary and the interior are opposite sets. Boundary is the outside, interior is the inside. Now, I have blown past a lot of proofs that are simply measuring geodesics and using the triangle inequality, using our definitions of peripheral, eccentric, boundary, interior. All of these proofs, in my opinion, are very readable. Why I didn't write them down? I think you should read them. I think reading them will help you with the homework assignments for this section. Questions? Oh, I have 4 lovely sections on stuff that isn't in this textbook, so I don't have assigned problems to go with it. But I have some really, really neat stuff about going back to traveling graphs and some of the other methods by which we can count and measure things that turn out to be driven by matrices. So I'm going to go back after chapter 13 and do matrix work. You've seen the matrices I'm going to use, at least some of them. We know what an adjacency matrix is. We used it for Prim's algorithm, the matrix version thereof. So I've got several very useful algorithmic behaviors on those matrices that I really would like to talk through. They're very well coded. They're very well documented. There are a lot of available apps that do all the work for us, but understanding where it came from turns out to be a foundational piece of both matrix work and connectivity and graph work. And it turns out to show up in, of all crazy places, shortest distances, shortest path from A to B. We measured our geodesics directly, but these are unweighted edges. What happens when I put weights back on my edges? Can I find appropriate shortest paths and shortest distances? But there are some really nice matrix algorithms. That's what happens after 13.1. I stole this from another book that was part of the applied computer science course that I taught for a couple of years. And I think that's why I'm going to teach it here, because it's really, really relevant to that. So we'll do 13.1, talk about domination in graphs, and then we'll go to matrix work. So I will see you all on Wednesday. Have a wonderful rest of your day.